So previously, we learned the notion of judgment, and we learned that for this judgment to make sense, we have to provide a corresponding set of inference rules. Without these inference rules, this judgment does not make sense. This time, let us see how to expand this set of inference rules by adding new inference rules, but without altering the characteristics of this system. As an example, let's consider the multiplication of two integers. Let's say 2 times 4 is equal to 8. So we can find a rule in the multiplication table that gives us the answer to this multiplication right away. But this rule in the multiplication table is just a convenient rule and is not strictly necessary, because if we don't have this rule in the multiplication table, we can always expand this multiplication into a series of additions. So we can calculate the answer by adding integer 2 4 times, but by employing the inference rule in the multiplication table, this one, we can instantly get the answer. So this rule in the multiplication table does not change anything in the arithmetic, but it is very useful for multiplying integers. Similarly, we'd like to add new inference rules to a set of inference rules given earlier, but without changing the characteristics. It turns out that there are two ways to add new inference rules. The first is derivable rules, and the second is admissible rules. Let's consider derivable rules first. Put simply, a derivable rule is a rule such that the premise the gap between this premise and conclusion can be filled with a derivation tree. So here we can bridge the gap between these two, premise and conclusion, with a derivation tree. Then we can think of this one as a derivable rule. So here's an example. Previously, we considered a system with two inference rules. 0 is net. This is 0 rule. And we have another inference rule, and net leads to successor and net. So this is a successor rule. Now we'd like to find a derivable rule from this system of inference rules. And here's an example. The premise is and net, and the conclusion is successor, successor, and net. Let's call this rule successor twice. Why is this rule derivable? It is derivable because we can always fill the gap between the premise. This is the premise. The gap between the premise and the conclusion. This is the conclusion. Successor, successor, and net. This is the conclusion. We can fill the gap between these two with a derivation tree. So here's a derivation tree. We apply the rule successor to have successor and net in the premise, and we apply the successor rule again to lead to the premise of the derivable rule. So If you are challenged to justify this derivable rule, you can always expand this derivable rule into this derivation tree. So therefore, it makes sense. Now, let's talk about admissible rules. There's no formal definition of admissible rules because an admissible rule is simply a rule that makes sense. What that means is that, let's say we have some premise, conclusion, and let's say this inference rule is admissible. So what that means is that if a premise holds, then conclusion holds. That's all. If you can somehow show that the premise always implies a conclusion, you can justify this rule as an admissible rule. Then here's a simple question. Suppose that you have a derivable rule. Is this admissible? And the answer is yes, because you can always justify derivable rule. Remember that a rule is an admissible rule. I mean, an inference rule is admissible if you can somehow show that the premise implies the conclusion. And for a derivable rule, it's very easy because you can always present a derivation tree that bridges the gap from this premise to the conclusion. So derivable rule always makes sense, so therefore it is admissible. What about the converse? The converse is admissible rule derivable rule? And it turns out that the answer is no, for good reason. We can actually find a counterexample where the inference rule is admissible, but it's not derivable. So here's an example. Let's consider this inference rule. Successor and net is the premise, and the conclusion is and net. So let's call it this a successor inverse. So this is basically the opposite of the inference rule successor in the original system. So we inverted the premise and conclusion, and we obtain this successor inverse rule. Let's first show that this is admissible. Remember that there is no formal definition of admissible. This inference rule is going to be admissible if we can somehow show that successor and net holds then and net holds. That's all. It's up to you how to prove this statement. And why is it that this statement makes sense? Let me draw the system, the original system. So we have 0 is net, this is 0 rule, and we have and net leads to successor and net. This is a successor rule. Now suppose that this judgment holds. We have a proof of successor and net. Then according to the inference rules in the original system, the only way to prove this judgment is by applying successor rule. There's no other way, because this is the only inference rule where the conclusion matches the conclusion matches the judgment that we'd like to prove. So if this is provable at all, then the last inference rule must be this successor rule. Then the premise must be and net. So what that means is that if we have a proof of this successor and net, we have some derivation tree that looks like this, and the premise of the last inference rule is and net. Therefore, we must have another smaller derivation tree that proves AND-NAT. So we can always extract a smaller derivation tree that proves AND-NAT, which means that this judgment always implies this smaller judgment. So according to the original system given here, this statement makes sense. Now let's turn this thing into an inference rule. This thing means successor AND-NAT leads to AND-NAT. So let's call it this successor inverse rule. So this rule makes sense. Here's our proof. So this rule makes sense, so it is admissible. Now, let me summarize the situation here. So this is the original system, and this is admissible. The question is this derivable? And the answer is no. This is not derivable because according to the inference rules given here, a derivation tree always looks like this. If you have, for example, successor AND-NAT, then the premise always smaller than the conclusion. It must be AND-NAT or something like this. So if you go upward, you will see always a smaller judgment than the conclusion. But in this case, the premise is strictly larger than the conclusion. So there can be no derivation tree that fills the gap between this premise and this conclusion. So it's not derivable. So now we have witnessed an inference rule that is admissible but not derivable. So back to the question, is an admissible rule always derivable? And the answer is no. Let's further investigate the properties of derivable rules and admissible rules. An interesting property of derivable rule is, let's say we have a system here, system of inference rules. And according to this set of inference rules, let's say we have some derivable rule. This is derivable. Now, let's expand this system of inference rules with new inference rules. So we started with this set of inference rules. Now we have this expanded set of inference rules. We have added these new inference rules. And the question is this rule still derivable? So the question is, this is still derivable? And the answer is yes, this is still derivable, even in the presence of these new inference rules. And the reason is simple. This rule is derivable with respect to this set of inference rules. What that means is that this derivable rule can be expanded to a derivation tree composed of applications of these inference rules. Now, the system has expanded with this new inference rule, and still this is a valid derivation tree because it's just a matter of reusing these inference rules. In other words, we can just ignore these new inference rules and still this is a valid derivation tree. So even if this set of inference rules is expanded with the new inference rules, this derivable rule, stays derivable. What about admissible rule? The question is, we start with this inference rule, system of inference rules, and we know that this inference rule, let's just say this 0 is NAT, and we have successor n is NAT if n is NAT. So we start with this inference rules, And from these inference rules, we can show that this rule is admissible. Successor and net implies and net. This is successor inverse rule. This is the successor rule. This is zero rule. So currently this rule is admissible. Now the question is, what if we add new inference rules here? So the system of inference rule expands with the new inference rules here. This is new inference rule, whatever it's gonna be. And the question is, does this inference rule continue to be admissible? And the question is, this is the question, and the answer is no. It depends on the new inference rule that is added to this system. Remember that in the case of a derivable rule, it doesn't matter, no matter how many inference rules are added to this system, a derivable rule stays derivable. But that's not the case for admissible rules. So here's an example. Let's add some weird inference rule like this one. Successor and net is provable if n is 3. So this is a bizarre rule. Now we expanded the system with this new inference rule. Then this rule, which was previously admissible, is no longer admissible because now successor and net does not necessarily imply and net, because now we have another chance of n being 3 instead of net. Without this inference rule, then successor and net always implies n being net. But with addition of this inference rule, successor and net might imply n3. So this does not hold anymore. So with the addition of this inference rule, this bizarre inference rule, this rule fails to be admissible. So the answer is no. So admissible rules should be revisited every time you expand on this system. So what that means is that this is a system of inference rules that you start with. And with respect to this system, let's say R, this inference rule R is admissible. Later, you expand this system with another inference rule. So you add new inference rules here. Then you have to revisit this inference rule, this admissible rule, and check again for its admissibility. Because depending on the new inference rules added here, this rule might fail to make sense. So that's the price that you have to pay for using admissible rules.